So here's the thing about these concentrations of these hydrogen ions and hydronium ions and hydroxide ions that we have. They are extremely small numbers. On the last practice, we got one that was like 10 to the negative 13th power for molarity. So these are somewhat awkward, somewhat just not the right size for us to use very well, and they tend to vary very dramatically from 10 to the negative 13th up to like 1 or 2, and so it makes sense and it's helpful to use a logarithmic scale instead. And we're going to call this, there are two we're going to use to start off here, the pH scale and the pOH scale. You've probably heard of the pH scale in terms of measuring acidity. You might not have heard of pOH, but they both do the same thing. That prefix P means negative logarithm of, and then H indicates that we're talking about the hydrogen ion. So it literally pH means the negative logarithm of the hydrogen ion concentration. And so it is going to be logarithm base 10 for these cases, not talking natural logs. So pH is the negative logarithm of the hydrogen ion concentration. So that's how we do it. pH is equal to negative log base 10 of H plus concentration. So we would expect to see the pH increase as H plus decreases because it is a negative for the log that's right there. So typically we'd say that high pHs mean that it's not very acidic because it would have a very low H plus ion concentration. Remember, that's what Arrhenius said, is that if it's an acid, it has hydrogen ions, H plus ions floating around, and so if we had more of those, it would be more acidic. We had more of those, we get a higher concentration, lower pH. On the other hand, if you had a very small concentration of H plus, say because you had a lot of hydroxide ions, remember that's how that sort of works. We put a base in here, we have fewer H plus ions, we'll get a lower concentration, which means a larger value for the pH. And so higher values of pH mean more basic, less acidic. Lower values of pH mean more acidic. So we did find earlier that if we had neutral water, just plain old water, no acid, no base, just water in here, the hydrogen ion concentration, if it's at 25 degrees Celsius, is 1 times 10 to the negative 7th molar. So let's figure out what pH we get for that. So we take the natural log, or not the natural log, sorry, the log base 10 of 1 times 10 to the negative 7th, which is just the, since it's base 10, it's just the exponent here, negative 7. So it's going to be the negative of negative 7, which is just positive 7. And so a neutral solution would have a pH of 7. That's neutrality. And so since we said that pH-wise is that higher pH meant more basic, lower pH meant less basic. Neutral we just found is at 7. It means if the pH is lower than 7, it's acidic. If the pH is greater than 7, it is basic. And the pH scale generally varies from 0 all the way to 14. It can actually go a little bit on the negative side. It can go above 14 in certain cases, but pretty much everything you're going to run into is going to be between 0 and 14. With 0 being the most acidic, so like battery acid might be close to a 0. The acid in your stomach's about a 1. Lemon juice a 2. Orange juice a 3. You might have coffees a little bit acidic, a 5. The saliva in your mouth is a 6, which is one of the reasons why you need to take care of your teeth. Pure water we said is a 7. Seawater a little bit basic. Baking soda even more basic. Hand soap, remember we said things bitter and slippery tend to be bases, and of course soap would fit that. And so you can see those down there. You get a little higher. Ammonia has going to have a pH of about 11, so it's very basic. Bleach even more. Oven cleaner extremely basic, and then sodium hydroxide all the way to 14, extremely basic here. Now, so this pH does vary based on concentration somewhat, and so you can't just say, well, lemon juice is always this, but it is a good scale to give you an idea on measuring things. And so the colors they're giving here, you can see we go from red down to the purplish blue here. These would be the color that an indicator would turn if it was exposed to something of this pH. And so that's what we sort of are looking at there. Now, one thing to remember, this is a logarithmic scale, and so that means every time you go up by 1 on the pH scale, the value is changing by a factor of 10. So something that had a pH of 5 compared with something with a pH of 6, it's not that the 5 is 1 more acidic, it is 10 times the concentration of H plus ions more than a 6. If you went from a 6 to a 4, that's 100 times different. There are 100 times more H ions or hydronium ions in a 4 4 pH substance than a 6 pH substance. So just remember, those are logarithmic. They go by factors of 10. So as we said, solutions with a pH less than 7 are acidic. If they're going to be greater than 7, they're basic. If they're equal to 7, they're neutral. Okay. Keeping in mind, of course, as we've said multiple times here, this is true only if we're at 25 degrees Celsius. If you change the temperature, it changes kW. It changes kW, it's going to change the values that are here. When it's not at 25, 7 is no longer neutral. It may adjust up or down depending on how the temperature changes. And so you can't necessarily do this to fit the scale exactly unless it's at this temperature. If it only varies by a small amount from that temperature, it's not going to make a huge difference, though. Now, similar to pH, pOH is a negative logarithm base 10 of the hydroxide ion concentration. You can see it in there, pOH, negative logarithm of hydroxide, so the implied negative that's up in there. And so we define it like that. pOH is negative log base 10 of hydroxide concentration. We said the concentration of hydroxide for plain old water is also 1 times 10 to the negative 7th, so it means the pOH of neutral water is also 7. So neutral water, pH is 7, pOH is 7. But this time is that since we're measuring hydroxide concentration, if we had a higher hydroxide concentration, it's a more basic substance, then we would have a higher value of the hydroxide concentration and a lower value of the pOH. And so if something has a pOH that's less than 7, it's going to be more basic. So it's sort of backwards from each other. It sort of might make sense. If you had a pH, high pH means more basic, low pH means more acidic. High pOH means more acidic, low pOH means more basic, with once again, neutral is 7 for both scales. So both scales end up with the same neutrality point here. So lower pH means more acidic, lower pOH means more basic, but how do these things actually relate to each other? There has to be some connection because they both came from the same formula. Well, let's start off with that. Let's look at our kW expression. So we said 1 times 10 to the negative 14th is equal to our hydrogen ion concentration times our hydroxide ion concentration. Well, let's take the natural log base 10 of both sides. So we get not natural log, let's take the log base 10 of both sides. So we have log of 1 times 10 to the negative 14th equals the log of the product of the hydrogen and hydroxide concentrations. Well, logarithms, remember, if you multiply two things in a logarithm, it's the same as adding those two. And so we can say that this is log hydrogen ion concentration plus log hydroxide ion concentration. Let's multiply both sides by -1, so we get a little negative sign that's out in front of each one of these. Well, what do we know? Log of 1 times 10 to the negative 14th, that's just going to be negative 14. A negative times negative 14 is positive 14. Negative log of hydrogen ion concentration, well, that's just something called pH. And negative log of hydroxide concentration, that's just pOH. So what we found is that the sum of the pH and the pOH is 14, at least for solutions at 25 Celsius. So if you know what the pH is, you can calculate what the pOH is. You just subtract the pH from 14, it gives you the pOH. If you subtract the pOH from 14, it gives you the pH. So really, we can figure out the other one by just figuring out which one's easier to solve for. If you know your hydroxide ion concentration and you need to know pH, go ahead and use the hydroxide ion concentration to find the pOH and then subtract it from 14 to get the pH. If you know what the hydrogen ion concentration is, then you're looking for pH, just go ahead and solve for pH. So it really depends on which one you have available. You can sort of use that to pick the most appropriate technique. So let's take a look at one. We have 2.1 moles of HClO4, which I believe is that perchloric acid? Is it perchloric acid or chloric acid? I don't have it written in front of me right now. But let's just write out what this is going to look like. So we have HClO4. It's going to react. It's going to decompose. It's going to dissolve in water. It's going to go into aqueous solution and form an H plus ion plus a ClO4 minus ion that's out there. Just a 1 to 1 to 1 mole ratio, quite nice here. Of course, keeping in mind in reality they aren't going to form H plus ions, they'll form hydronium ions, but the concentration is the same. We'll simplify it out like this. And so 2.1 moles of this, or add 24 liters of water, what is the pH of the resulting solution? So to find the pH, we need to know the hydrogen ion concentration. So let's see if we can figure that out. So we know the number of moles of HClO4. If we could figure out how many moles of H plus we have, and we can then use that with the 24 liters to find the concentration. So 2.1 moles of HClO4. Set up our table. We want to go from moles of HClO4 to moles of H plus, and that's just a 1-to-1 ratio right there. So we've got that without too much trouble there. So we would then, well, it's just going to be 2.1. We actually should have known that right off the bat. So 2.1 moles of H plus. So the concentration of hydrogen ions should be equal to 2.1 moles of H plus over the volume of this, so 24 liters. So when we do that, this ends up being right at 0.0875 molar. All right, so since we have that, now we're looking for the pH because we have the hydrogen ion concentration. We know the pH of this substance. Whoa, I don't know what just happened there. So the pH of this substance right here, oops, is going to be equal to negative log base 10 of 0.0875. Now, so doing this here, log of 0.0875 is going to be negative 1.058, which means our pH is just 1.058. So since we know that this value is less than 7, we know it's going to be acidic, which would make sense because we're adding an acid to it. And 1.058 is extremely acidic, so this is a very, very strong acid that we have here. Second question is, what's the pOH? Well, good news is that's easy to figure out because remember our little trick is that we know that the sum of the pH and the pOH is going to be equal to 14. So we just say 14 equals 1.058 plus pOH. Solve both sides, just subtract the 1.058 from both sides. And then that's going to give us our pOH of 12.942. 12.942 unrounded. Sig fig wise, 2 sig figs, 2 sig figs. So that means that has 2, that has 2, that has 2 right there. This will end up with 2, so this will just be a pH of just 1.1 and a pOH of 12.9. All right, so that would be how you'd go about solving for pH and for pOH for a solution. So let's say we have another problem here. To neutralize a certain base, 450 milliliters of a 9.5 pOH hydroiodic acid solution are needed. How many grams of hydroiodic acid must be added? So let's go ahead and take a look here. So it's hydroiodic acid. That's going to be just HI. It's going to break down into H plus iodide right there. Let's see, we're trying to find, let's see, how many grams of HI must be added. So we're trying to find the grams of hydroiodic acid. Now, in order to figure that out, we're going to need to know what the concentration of the hydrogen ions are. Because we know the concentration, since we know the volume, we can use that to find the number of moles of hydrogen ions. If we know the moles of hydrogen ions, we can use that to find the moles of hydroiodic acid and use that to find grams. So really that's what we want to do. We want to figure out what this hydrogen ion concentration is. But we don't have pH, we have pOH. So let's find pH first. So 14, it'll just be subtracted off, right? 14 minus 9.5 should be our pH. And 14 minus 9.5 is just 4.5. All right, so we have a pH of 4.5 for this. So we know that 4.5 is equal to the negative log of our hydrogen ion concentration, H plus, right there. So because it's log base 10, we can undo the log by raising both powers, both 10 to those powers here. Let's go ahead and move the signs first, but then we'll just take 10 to that power, 10 to that power right there. That's going to cancel that off right there. 10 to the negative 4.5. Let's see, what's that going to end up being here? That ends up being 3.1 3.1623 times 10 to the negative fifth molar. That's going to be our hydrogen ion concentration. All right, so now that we know that, we have our concentration. We need to find moles, and so we know that that concentration, 3.1623 times 10 to the negative fifth, should equal to the number of moles, which we don't know. We'll call it X moles of H plus over the volume, 450 milliliters. We want that in liters, so I'll do 0.450 right there. Multiply the 0.450 up to both sides. And so doing so ends up being that X is 1.423 times 10 to the negative fifth moles of hydrogen ions. All right, so now that we have that, we're trying to find grams of HI. So let's just go ahead and set up our table. We want to go from moles of hydrogen ions to moles of hydroiodic acid, and that's going to be just a 1-to-1 ratio in this particular case. Then we want to go from moles of hydroiodic acid to grams of hydroiodic acid. Iodine is, what is that, 126.9 plus hydrogen 1.01, so 127.91 in 1 mole. So moles H plus are canceled, moles iodine, hydroiodic acid are canceled. Do the math on this one, and it ends up being 0.00182 grams of hydroiodic acid. So not much at all. Sig fig wise, looks like 2 sig figs, so 0.0018 grams. So we're talking here, what is that, 1.8 milligrams? So tiny amount. So you can see that it doesn't take a whole lot of these acids to be able to end up with a reasonable concentration, because this was a pH of 4.5. That's pretty acidic. It's not super strong acid, but that's like those in like the lemon juice to orange juice range, and we didn't need a whole lot of this at all just to be able to get the right concentration here. So last one. What concentration of hydroxide ions will be found in a solution with a pOH of 3.3? Now, in the past, when we've done these problems, we've always used our pOH plus pH equals 14 to solve this out because we've been looking for hydrogen ions. But here, we're looking for hydroxide, so it doesn't make sense to do that. Now we're just going to go ahead and use our pOH, because if we want to find concentration of hydroxide, the pOH will be right what we want, because we know our pOH is equal to negative log of our hydroxide concentration. So really, if we're looking for that, we just need to plug it in and solve. So pOH is 3.3, no reason to take anything different, equals negative log of hydroxide in here. Once again, move our signs over, 10 to the power of this whole thing right up there. So those are going to cancel off right there. 10 to the negative 3.3 ends up being 5.01187 times 10 to the negative fourth molar. And so that should be equal to our hydroxide concentration, which is what it asked for right here. Sig fig wise looks like 2. So this would just be 5.01 times 10 to the negative fourth molar. Hydroxide. So that's how we go ahead and work that out.